Thank you. So my name is George Argyros, and I'm going to present our work called Back in Black towards formal black box analysis of sanitizers and filters. This joint work with Ioannis Stais from University of Athens, my advisor Angelos Keromitis from Columbia University, and Angelos Kagias from University of Edinburgh. So the motivation of our talk is that sanitizers and filters are fundamental building blocks of securing applications. So think about any code injection attack like cross-site scripting or SQL injection. One of the most basic ways of defending against those attacks is to take an untrusted input and either sanitize it, that is, turn it into a trusted one, or reject it if it's deemed malicious. And many times it is necessary when we analyze such applications to do it in a black box manner. So to do it without access to the source code. And there are multiple reasons for that. It might be a policy case, just like in penetration testing, or it might be too expensive to gain access to the source code. An example of that is like hardware testing. An important property of filters is that often they have to be simple and they have to be fast, because we sanitize a lot of inputs, so we have to do it in a quick manner. So this gives us the opportunity to model these functions as formal models like automata. And on this talk, I will focus on regular expression filters. However, in our paper, we have many results on sanitizers too. So what are regular expression filters? Regular expression filters work as follows. They take an input and they pass it through a regular expression. If a match is found, they would reject the input as malicious. And they used to be widely employed for defending against attacks. However, they turned out not to be very robust by themselves. And as such, from now on, they're mostly used as parts of larger software packages, such as web application firewalls, intrusion detection systems, and others. And an important property of regular expression filters is that we can represent them as deterministic finite state automata. So the fundamental question that we would like to address is, can we efficiently infer such filter? Can we learn the structure of such filters by querying them? And to address this question, we have to take a look at a specific learning model called exact learning from queries. So in that model, it's an active learning model in which a learning algorithm is able to actively query the target machine, the target automaton, with two types of queries. The first type is called a membership query. In that query, we send a string, an input to the machine, and we get back whether that input is accepted or rejected by the target automaton. On the second type of query is more complicated. We send in a model, a hypothesis that we learned, and then the query will answer back if that hypothesis is correct. And if it is not, it will give us an input in which the hypothesis and the target machine are behaving differently. So in that space, in that model, there is a very popular algorithm for learning deterministic finite state automata, which is called the L-star algorithm. That algorithm works as follows. We first start with our initial hypothesis being an initial state, just a simple state. And afterwards, we will test all transitions from that state and see where they are going. And there is a way to do that. And at some point, we will come up with a valid hypothesis, a valid automaton. And when we do that, we will test that automaton for equivalence. We will do an equivalence query with that hypothesis. And the counterexample that we will get if the hypothesis is incorrect will provide us access to further undiscovered states in the target machine. And this way, eventually, we will come up with the correct hypothesis, the correct automaton, and learning will terminate. Now, notice that since we check all transitions from each state, this is really inefficient to do for large alphabets, if we have a large number of symbols. And regular expressions usually have a very large number of symbols. They could range across the whole Unicode set. So we want something that works with large alphabets. And to do that, we examined what is called symbolic finite state automata, or SFA for short. And symbolic automata, while classical automata have to explicitly state each transition, in symbolic automata, we group transitions into predicates. And these predicates, which we call guards, are basically sets of symbols that are grouped into a single transition. So this looks like it exactly addresses our problem. It compresses the transitions into a single transition. So what we would like to do is to use symbolic automata to infer regular expression filters. But in order to do that, we had to address a number of challenges. The first and most fundamental challenge is that the alphabet might be infinite. So there is no way that we can explicitly test all transitions. And furthermore, whenever we want to do an equivalence query and we get back a counterexample, we cannot assume now that that counterexample is due to an undiscovered state as before, but it might be due to a wrong guard that we generated. So we came up with an algorithm in order to learn symbolic automata, and this algorithm works as follows. Again, we start with an initial state, and we don't test all transitions. We test a sample of transitions. So we might test 2 symbols, say. And then this sample will be fed into a new algorithm called guard-gen algorithm, which will basically take the samples as a training set, and it will produce the guards for that specific state. And this way, we will generate a hypothesis. And after that, when we check that hypothesis for equivalence, we came up with a novel counterexample processing method that basically can distinguish between the 2 cases that I mentioned before, and thus we can eventually learn the target automaton as a symbolic automaton. And this is guaranteed always to converge into the correct automaton under some natural assumptions of the guard generation algorithm. So given this algorithm, the next question that we have to ask is how realistic is the learning model that we've built our algorithm on? So is exact learning from queries a realistic model? So let's have a closer look at that. In exact learning from queries, as we said, we can do 2 types of queries, membership queries, in which case, in a practical setting, we can simply test whether a specific input is accepted or rejected by the target filter, and then we have to do equivalence queries. And that's a problem, because there is no way without having an exact knowledge of the filter to answer that question. However, by definition of the problem, we don't have that knowledge. So what do we do about that? In order to solve this problem efficiently, we slightly modified our problem in what we called grammar-oriented filter auditing. In that problem, which is, I will also refer to as GOFA for short, we have an attacker which wants to obtain some confidential information. That attacker is in possession of a context-free grammar G. That context-free grammar is defining a set of attacks. So you can imagine that that context-free grammar might have some JavaScript code definitions or for cross-site scripting or some SQL code for SQL injection. And now we have a filter protecting the confidential information. And that filter works by having a regular expression. And basically, whenever the attacker sends in an input to the application, the filter will check if that input matches the regular expression, and it will either reject it or it will return the normal output. So the goal of the attacker is to find a string that belongs to the set of attacks that belongs to his context-free grammar but does not being rejected by the filter. And even if we know the size of the target regular expression, this may require an exponential number of queries in the worst case. So how are we going to solve this problem in practice is as follows. In an ideal world where we had both the context-free grammar G and the target filter F, we could just compute the set of strings that is not rejected by the filter. That is a complement of the filter F. And then using some simple automata theory algorithms, we can compute the intersection of the grammar with the filter and check if there is any string that bypasses the filter from the grammar. So this can all be done efficiently. However, in practice, the filter is not available, as we said. So what we can do is that we can infer a model for the filter and use that instead of the actual filter. So let's see how this works. So we have our same setting, but now our attacker is also equipped with the symbolic automata learning algorithm. And he has to be able to perform the 2 types of queries that we mentioned. So a membership query, as we already mentioned, is simply sending that particular string that we want to query in and testing if it is being rejected by the filter or not. Now, when the algorithm produces a hypothesis, we simply do the algorithm not with the actual filter. So we try to see if there is an attack that bypasses the hypothesis, not the actual filter. And if we don't find such an attack, we terminate the algorithm, and we stop there. However, if we find such an attack, then we send it to the target server. If that attack is rejected, then notice that this is a counterexample for our hypothesis, because by design, this attack should bypass the filter, and thus it bypasses the model, and thus it should bypass the target filter. If the attack actually bypasses the target filter, then we basically won, because we solved the problem positively. So this allows us to actually implement equivalence oracles with a single membership query. And of course, it is not a complete solution, but soon I will talk about how efficient it is in a practical setting. So going into the evaluation of these algorithms, we have to decide how are we going to evaluate them. And we chose 15 regular expression filters from popular web application firewalls. These filters have a range of sizes, both regarding states and transitions. And for an alphabet size, we chose an alphabet size of 92 symbols, which contains most printable ASCII characters, and therefore we are able to express a large range of attacks using this alphabet. And the first question we will ask is how efficient is SFA learning symbolic automata versus learning deterministic finite state automata. And it is surprising that we found that we had huge increases in the number of queries. So we noticed that on average, SFA learning would require 15 times less queries than the classical DFA algorithm. However, we have an increase in the equivalence queries that they're being used because we have to also take into account wrong transitions being generated. And an important point here is that the speedup is not a simple function of the automaton size. And going next, I would like to also point out that the DFA algorithm is prohibitive to use over the network for even automata with around 150 states. It would require around 2.5 million algorithms. So having a speedup in that case is very important for the practical setting of the problem. Next, we would like to evaluate our grammar-oriented filter auditing algorithm. And the first experiment we performed is we assumed that the grammar does not contain a string that bypasses the filter. At that case, we would like our algorithm to provide a good approximation, to actually function as an equivalence oracle and provide us with a good approximation of the target filter. And the important question here is, what is the correct grammar to use for that algorithm? And we chose to use as an attack grammar the filter itself. The reason to do that is that basically the filter itself is intuitively a maximal set that does not contain a bypass for the filter. So if you think about it, the filter itself contains all the information that we need in order to infer the target filter, but does not contain any string that will bypass the filter. So in this setting, we found that learning using SFA in the context of grammar-oriented filter auditing gave us even further increases in the speedup gains in our setting. So we have on average 35 times less queries. And in terms of states recovered from the target filters, we saw that both the DFA and the SFA have similar states recovered. So DFA recovers 2% more queries than SFA, and that's because it basically brute forces all transitions. But that's the trade-off there is that we have to look to use 35 times more queries, which is basically impractical. And a final point that I would like to say here is basically if that grammar-oriented filter auditing algorithm can be used in order to evade web application firewalls. So for that setting, we handcrafted a grammar with valid suffixes of SQL statements. So you can think of an SQL statement that is valid, and then what can we do after a point to complete the statement with valid suffixes. And that basically simulates an SQL injection attacks. And what we did is that we tested our algorithm against live installations. So we didn't test it against individual regular expression filters, but against live installations of Mod Security and PHP IDS, which are two very popular web application firewalls. And I want to point out here that both of these systems include non-regular anomaly detection components. So it's not that we have a purely regular system here. And we were able to find bypasses for both firewalls. We found an authentication bypass using the like operator, and we also find an attack which can be used to retrieve data. And both of these attacks were acknowledged by the mod security team. So to conclude, SFA's symbolic fine state automata provide a nice way to infer regular expression filters by avoiding brute forcing transitions while learning. And also, we found out that the same algorithms can provide insights for non-regular systems. So while we cannot show that they can learn these systems completely, this is impossible if they are non-regular, they can provide nice approximations which can be used for practical attacks. Also, I would also like to point out again that we have similar techniques derived for sanitizers, that is, functions that take the input and convert it to a non-malicious input. And also, there is a large space for future work in this area. So our guard-gen algorithm, the algorithm that actually learns the transitions, is a very simple heuristic for regular expressions, and we were able to gain huge speed-ups this way. However, we believe that there are many other things that one could do in that area. And finally, I should say that we envision the context of our algorithms to be in assisted black box testing rather than a point-and-shoot tool. So even in the attacks that I presented, we basically obtained an abstract valid statement in a context-free grammar, but this then should be converted in a concrete attack. And this is something that an auditor should do by himself. And also, we expect if the models that our algorithms infer are inaccurate, in case we don't find an attack, then we expect the auditor to be able to inspect these models when they are converted back to regular expressions and maybe correct any inaccuracies and further assist the algorithm to proceed. And with that, I would like to thank you all for your attention, and I will take any questions now.
Okay. All right. So questions?
Hello. Really interesting work. I'm curious, it seems like some of your DFAs are quite small, like 16, 20 states. Mm-hmm. Did you actually take a look at the model inferred and try to determine if it was being minimized or if there's a correspondence? That's a common thing in DFA learning.
So this algorithm, basically the DFA and the SFA learning algorithm, they will infer minimal automata. So the DFA learning algorithm, when it will infer an automaton, then automaton will be minimal. So if you're talking about so in our experiment, like not in the grammar-oriented filter auditing setting, but in the original setting, we simulated equivalence queries to actually count the total number of queries used by both algorithms. So at that setting, we actually inferred that, we stopped whenever we had the correct hypothesis. So we knew that the automata inferred are both minimal and correct.
I meant more actually just looking at the regular expression.
Looking at the actual picture?
Yeah.
Oh, I mean, we did that, but for some very small automata, like, 10 states or something like that. So that's usually very simple pattern matching. They will match a string or something. So what was your question on that, if they look minimal or?
If they look the same, if you're actually learning the same regular expression that the person had implemented to do either sanitization.
So we didn't convert it back to regular expression. We just learned the automata. So if you want to convert back to a regular expression, that's a different problem, and it's also a hard problem. So you have to address that. You can do it, but it might blow up. So learning a minimal regular expression is a very hard problem.